sort of measurement. Okay, so we are just giving focus on that kind of measurement that doesn't require an invasive procedure. So that is why whatever may be the signal, you can measure ECG. Probably you have heard of the term ECG. It is very silly to ask that, but you should know. But okay, I have to ask anyone who doesn't know what is an ECG? ECG সবাই জানো তো?
হ্যাঁ স্যার।
Yes sir.
তোমাদের সবাই জব পেয়েছে? এখনো অবধি placed most of you?
হ্যাঁ স্যার।
Yes sir.
Medical test হলে দেখবে, whatever may be the company, if you are going through a medical test, that ECG is a must. Okay, and in Bishad sir's part, that is in the part that will be covered by Professor Bhattacharya, in that part you will be learning in details how that biopotential or bioelectric signals they are generated. We are planning to measure that, and if we are measuring that kind of a signal, even nowadays EEG signals are there. Have you heard of EEG, electroencephalogram, the instrument?
Yes sir.
That measures the brain signal. Because of the brain activity, the electrical signal that has been produced, that is measured. Similarly, EMG is the electromyogram. Probably you haven't heard. Maybe some of you have heard. Electromyogram means because of the muscle movement, some similar kind of signal, electrical signal may be generated in our body that can be measured. So even when we just move our eyes, some electric potential can be generated, that is called electrooculogram, EOG. So there are so many signals that we can measure. But the problem is, what is the signal strength? What is the actual amplitude of the signal? In many cases, that signal is of very small magnitude. It can be millivolt, that is quite high if it is millivolt. Usually that can be lower than millivolt and may go up to say microvolt. Okay, so that is why these signals are of very low magnitude. If that is the signal is very low magnitude, then accurate measurement is very difficult, because some sort of glitch, some sort of other signal that is present in the ambient, that may change your signal significantly. The error in measurement will be very much. So that is why the noise, elimination of noise is an important issue. That is why in our first class, we are dealing with this noise. Now, if you have any question till now, you can ask me. এই অবধি কোনো question থাকলে জিজ্ঞেস করতে পারো। Akhil, if you have any question till now, you can ask.
No sir, I don't have any questions.
Very good. We always prefer those who don't have questions. Okay. So already you have also understood that you are in the first year, last semester, final year, last semester. So already you know all these things. Okay, let us proceed. So now there are different kinds of noise that may hamper our measurement, that may affect our measurement, biomedical signals. I have given, that is, say, number one, that is a thermal or Johnson noise. Probably you have heard of in many other any other course. Short noise, flicker or 1/f noise, offset or drift. Offset noise, that is also known to you in your op-amp or in your ADC DSC errors. and environmental noise. Okay, so mainly we are discussing these four, and why we are discussing this now, not earlier, because of the reason that now the signals are of very low magnitude. Okay, we cannot increase that at our own sweet will. We can increase, but at the same time noise will also get increased. So therefore denoising is an important issue. First of all, let us know what are the noise we have to remove. So thermal noise or Johnson noise, the thermal noise and Johnson noise, that is because of the, say you are having one resistance, say you are using one resistance. Now that resistance, that means there will be some flow of electron if the resistance is carrying some current. So resistance, if it is having something or measuring something through some current will be flowing through. So therefore I am drawing, this is a resistance. So if it is a current flowing through I, if we magnify this resistance, it will look like this is the, say, wire, and there are electrons, they will be flowing in some direction. Now electron, that is the one quantum of charge. So whenever the thermal agitation occurs, whenever temperature changes, there will be thermal oscillation, etc. So therefore the current, we say it is a uniform current I, but if we look into the microscopic view of this, then we do not feel that it is a, say, a continuous flow of current. The current is granular, sort of granular, and each granule is called, we can think of an electron. So that granule means the current will flow like a quantum, and that particular, because of thermal agitation, there is no guarantee that at every instant of time equal amount of electrons they will be passing through. So there will be some oscillation in the current, as well as that means that there will be some voltage drop across this, and that voltage drop, even if we are saying that current is if it is 1 ampere, then the effect will be very less. But if the current is small, that fluctuation because of the thermal agitation of electron, that will be significant. So whatever may be the thing, your current may be a constant one, but because of the thermal agitation of the electrons, the current you are measuring at the end or one terminal of the resistance, that may not be constant one, because of this thermal agitation, because of this granular nature of the current. So that is why you are measuring a voltage, say I into this R is fixed, say I, you are saying it is fixed, but voltage will no longer remain I into R, because I is this kind of a flow of granular electron. So therefore the voltage drop changes with time. So even you are not going to get a constant voltage, rather than you are going to get an oscillatory voltage. So that is the source of the thermal noise. And you can understand that this kind of a noise, that has something to do with that electron flow, and that can be modeled using your, say the Boltzmann and other distribution of flow of electrons, and from that you can find that this is the overall effect of that noise, thermal noise. Okay. Actually the origin of this is from sort of a classical theory, but we can have this equation, but actual representation should come from the quantum theory. So we are not going to deal with that, but you can think of, in your class 12 course, probably you have forgot it right now, say equipartition of energy in the thermodynamics, half kT in part degrees of freedom, that is the energy. Can you remember this? Anyone? Slide. that half kT, say this K is Boltzmann constant, T is the absolute temperature. So you can think of that energy is some sort of product of this. Now power is energy by time, it is power. So power is here, you can think of, if we multiply frequency is cycles per second, so therefore power, we have to multiply it by some frequency. So half kTf frequency is sort of power, and power in across a resistance is V square by R. So therefore V will be equal to P into R, that root of. So from that, this RMS comes as this 4 kTr delta F. Okay. The scaling factor is 4. We are not dealing with all this, but why this equation depends on this Boltzmann constant, on this T, R, delta F? Apparently, you are trying to understand. From engineering point of view, you do not require that. We have to use this equation if it is required. So here, delta F is the range of frequency. That is, we call it a bandwidth of the frequency. And so more is the bandwidth, more will be the noise. So that is why this is a problem. And the problem is you cannot eliminate this. You cannot eliminate this noise. But from your random process class, you know, as this is having some random nature with some known distribution, so we can estimate that. So that is why all of the noise, even if you know it is present, you may not be able to eliminate that 100%. You can estimate that, and from that you can have a good estimate of your quantity that you are measuring. Okay. Another, this kind of noise that can also be there in presence of the capacitor, it is called the kT by C. And whenever the voltage fluctuates, this capacitor can also show some sort of this kind of noise. So this particular type of thermal noise is very problematic for resistors as well as for capacitors also. Sometimes in engineering we call it kT by C noise. Okay. So this noise, all the detailed derivation is not required. The empirical formula that we can use for our practical purpose. The similar thing happens in case of semiconductor devices, not only for the conducting resistors, the semiconductors also, their number of charge particles or charge carriers, they are small in number, even small for the low value of current. So again, that grainy nature of current that comes into play, and that is also called the short noise. But as the semiconductor and the conductor, the electron and charge carrier distribution, they are not same. So the equations are quite different and more or less same, but not exactly same. It is like this one. Okay. So again, this particular flow actual current we are trying to measure, the noise current will also, but as the semiconductor and the conductor, the electron and charge, whenever we are trying to measure a current or a voltage, this kind of a noise will be there. That means you are trying to measure a constant voltage or current, but we are going to get, say, an oscillatory or a sort of say you are going to try to measure, say with time, this is say a voltage, say it is a microvolt range. Ideally the voltage should be a constant one, but whatever you are getting is like an oscillation. Or maybe in case of ECG, you have seen the ECG. Say ECG is sort of a voltage waveform like this. You have seen in the cinema, in many cinemas, that those curves are shown on hospital scenes and others in the displays present there. But if it is having some noise, those oscillations can be there. So it is very difficult for the doctor to identify what is actually happening. So before looking into this, we have to eliminate the noise. So that is the purpose. One by F noise is very common, but very difficult. It is sometimes called flicker noise. What you can understand from 1 by F, usually it is very problematic because of the fact it is quite of opposite nature compared to the other kind of noise. You know, the noise, say for example, if our 50 hertz supply system is there, noise or harmonics that is of higher frequency. So usually we have a feeling whenever we say noise, it will be of high frequency, but not always. This noise is 1 by F noise. Okay, this 1 by F noise, that means it increases with decrease in frequency. So that is why it actually hampers mainly the electronic devices, and the exact nature, that exact model depends on the quantum nature. We cannot have any other way to explain it. So this is the nature of the noise. You can see usually in all of the frequencies, some noise will always be there. So some noise level will always be there in all frequency. And those kind of noise having all of the frequencies, what does it call? It is written there, you know, white noise. In your communication ke ager semester hoyeche na ei semester e ache? Oishani? Torshik, huh? Nasir mane last semester e hoyeche, okay. So probably you have heard of the white noise, channel noise, etc. Hoyeche, white noise hoyeche to. So why it is called white? No, Gaussian additive noise doesn't mean that white. Gaussian is the distribution.
Sir, because this noise is present for all the frequencies.
Yes, if all the frequencies are present in light, that gives us white light. So in that aspect, it is called white because all of the frequencies are there. So here, that flicker noise, sometimes it is called also the pink noise. Why it is called pink noise? Because it is towards the lower frequency, that means higher wavelength, that means toward the reddish color of the spectrum. So it is called a pink noise, not exactly red. That is why it is a reddish sense. But okay, that is only to understand, to make you feel that this is having a higher wavelength, that is lower frequency. Okay, it is quite different frequency than that of the actual pink color light. So nothing to do with light exactly. It is actually giving you the idea of the relative position of the wavelength. Okay. So 1 by F noise, it is again the reason of generation of pink noise. Why a system noise increases at very low frequency? That depends on the system, mainly dominant for semiconductor based devices, and the explanation should come from the quantum theory, not by any classical theory. Okay, so we are not going to do that. We are only trying to understand that from engineering point of view, how to eliminate that. So from like sort of a simple Bode plot, it looks like there is a corner frequency. So if we can plot it, if we can measure that what is the nature of the noise, and we can then think of a filter whose cutoff frequency will be Fc. So beyond that, all the noises at the low frequency, that can be eliminated. So here actually you should go for a band pass filter, isn't it? So low frequency, that should be removed, and also high frequency noise should be removed. So most of the noise are high frequency. So high frequency noise should be removed, but as well as if your 1 by F noise is there, you have to eliminate the low frequency noise also. There are different methods to eliminate that. We'll discuss in a short while. offset and drift, that is known to you. For example, if you are having, say, temperature variation, op-amps will show the offset error that can that has been changed with time. So you are expecting a signal like this. Maybe you are expecting a signal like this. Say there's a sinusoidal signal, but because of drift, the signal may go on like this. Okay. So just like with the presence of a drift which is varying drift with temperature, the signal may come up like this. So this kind of a offset and drift error can also be there. And also environmental noise can be anything. That can be, say, your ambient interference, etc. So we are not going to discuss environmental noise. Otherwise, if you have any question related to that, you can ask. কোনো জায়গাটা বুঝতে না পেরে থাকলে আমায় বলো। সপ্তর্ষি,
Sir, why is the flicker noise called flicker noise?
Actually, flicker is having a low frequency noise, so that is why it is called a flicker noise. Okay. Here it is actually 1/f. Sometimes it is called flicker because that particular noise amplitude that is varying with the frequency. It is not constant. Okay. So 1/f as well as flicker.
Okay.
Okay. Anything else? সবাই নিশ্চয়ই এখন লেপের মধ্যে শুয়ে ক্লাসটা করছো, তাই না? বিছানা থেকে নেমেছো? কেউ?
হ্যাঁ স্যার।
নেমে পড়েছো? ওকে, ঠিক আছে, ঠিক আছে, দেখা যাক তাহলে। So how to remove now these noises? One important thing is the grounding and shielding. You have heard this term, grounding. In case of high voltage applications, grounding is important. That will be covered in your high voltage classes, because power stations and other proper grounding is required. Here, whatever you have learned there, you have to, you'll see that we have to change it for the measurement. So grounding for power system and grounding for this kind of very small signal measurement, they are quite different. Okay. And shielding, say this is a wire and the wire is having some resistance. So shielding means you are covering the wire using a metal portion. This metal portion that is not connected to the wire, this is insulated from the wire, but it is like this. And usually the shield is grounded. Probably you have heard the term shielding, at least in your AC bridge. Shielding কতটা শুনেছো?
Yes, sir.
Probably during cable also you have heard it, isn't it?
Yes,
Cable এর উপরও shielding থাকে. So now tell me, what is the purpose of the shielding? How the shielding removes noise? বলতে পারবে কেউ? Shielding করলে, shielding means this portion is sort of a metal cover. Shielding means sort of a metal cover. So what is the purpose of this? See, বলতে পারবে কি? কনসেপচুয়ালি এগুলো একটুখানি ক্লিয়ার থাকতে হবে।
Sir, the metal cover absorbs the noise, that is electromagnetic radiation.
Okay, let us, yes, that is true, but let us discuss it in a bit detail. Say you are having, say we are discussing in two ways. One, we are having an electrostatic field. Electrostatic field, that means electric field that is stationary, not time varying. And then we'll be thinking of a time varying field, or we can think of an electromagnetic effect. So first of all, let us think of if a electrostatic field is there. You know the flux line that passes through the metal, because charge because of the charge always reside on the outer surface. So if you shield it, so the induced charge that may, and the body is grounded, so therefore even if there is a bound charge, that will be on the outer surface. So inward there will be no such effect. Inside the electric field will be zero. So even if you are having some electric field outside, the effect inside, that will be less. So there won't be any electrostatic effect also. That is the electrostatic shielding. Clear? এই অবধি বুঝেছো? Now for electromagnetic shielding, if it is an AC or electromagnetic wave, that is transverse wave, time varying, then what happens is that, see this wire, I am drawing an wire, it is a metal wire, say, and over the wire there will be some insulation coating or air outside. So from the metal portion up to air and towards the ground, the metal, air, then ground, then what is this thing? That will create one capacitor. This kind of capacitor, they are called stray capacitors. There will be so many stray capacitors. Okay. And you know, at high frequency, those capacitor effect will be much more, because 1 by omega c. So omega is high, the impedance will be low, so much more current will be drawn through these stray capacitors. So under AC, those stray capacitors you cannot eliminate. They will be there. And the effect, these stray capacitance will not be fixed. At different configuration, at different positions, this capacitance will be different, because C is, say, epsilon A by D. So D, A, that will be different in different positions. If you apply this kind of a shielding, what happens is that these stray capacitors, whatever it may be, their effect will no longer different in different positions. See, this body is grounded, so therefore the stray capacitors with respect to this metal resistors, etc., they will be same, fixed. So there will be some effect, but the effect will be fixed, or that can be predicted or eliminated or estimated. Okay. Clear? Bolo. And another aspect is that if this kind of electromagnetic field is there, if the cover is there, the strength that is affecting this resistor, that will be, the strength will be reduced somewhat, but not exactly eliminated. Say you are having one unwanted electromagnetic field here, unwanted electromagnetic field is oscillating. So what will happen? Within that inductor or conductor, there will be some induced EMF. So that induced EMF will act as a voltage drop across the conductor, and that will create additional voltage measurement. So you are measuring a constant voltage, but oscillatory noise will be there. So this is the source of the noise, because of the ambient noise, because of the ambient electromagnetic wave, time varying electromagnetic wave. বলো এই পার্টে কি কোয়েরি আছে? তো শিল্ডিং কেন বোঝা গেল? For two purposes, one for electrostatic field, other for the electromagnetic. The explanation for two things, they're quite different. বলো বুঝলে? কারোর কোনো কোয়েরি নেই?
Sir, stray capacitor এর সাথে কিভাবে মানে ব্যাপারটা বুঝতে পারলাম না।
স্ট্রে ক্যাপাসিটর মানে সে ধরো ইউ আর হ্যাভিং ওয়ান রেজিস্টার, তোমার ধরো সার্কিটে একটা রেজিস্টার আছে যার মধ্যে দিয়ে কারেন্ট ফ্লো হচ্ছে। সো হোয়াট ইজ দিস রেজিস্টার? It can be a metal film, thin film resistor, okay? So that metal or conductor, so above that there will be some insulation coating. Even if it is a bare conductor, then also air will be there. So whenever you are using a metal or something, if it is have something to do in contact with air, some metal, air, then ground, some capacitor will be formed. That capacitor you cannot see, that capacitor you cannot measure exactly, because at different position, if you place it over a table, so you are placing it over a table, so maybe the ground is far away, so the capacitor, the stray capacitance will be something else than if you are placing that close to ground. So at different position, this stray capacitance that will be different. So if you are measuring with the same experimentation at different places, different result will come, because the stray capacitor will draw some amount of current. That capacitor you cannot measure, you cannot see. Bujhle?
Yes sir, and the current will be high frequency noise current due to the EMF.
Yes, because if your noise is many cases that is high frequency, so high frequency the current will be more, because this at high omega that impedance will be less. Okay, so at high frequencies the effect of this will be more. Bolo. Any other question related to this? কি বললাম বোঝা গেল কি? Okay. So now this is a typical say connection. So this is your source. Say this is your say electrode lead. You are measuring ECG voltage lead, and that is a transducer that is sending some voltage to your measuring instrument. Now the connecting wires, they are having some shield, that is a metal portion. The shield is usually grounded. Now whatever you have heard in your power system, at say CSC is supplying, so at the source the CSC neutral is grounded, and your household thing is also grounded, isn't it? So your household supply is also grounded. Clear? So usually we prefer grounding at our own place also, but that is not very good for this kind of a measurement. Okay, এটা পড়েছো তো, নিউট্রাল গ্রাউন্ডিং থাকে, সে ধরো এদিকে গ্রাউন্ড করেছো, তোমারও এখানে আর কি এই লোড আছে, তুমিও বাড়ির এখানে এটা গ্রাউন্ড করলে, সো ইউ আর গিভিং দ্য সাপ্লাই। পাওয়ার সিস্টেম এরকম কানেকশন দেখেছো তো?
Yes, sir. Yes, sir.
But this is not very good in case of this kind of a measurement. Usually in power system we do not prefer that floating ground, but here in case of measurement we prefer floating ground. Why? See here, if it is grounded, then what happens? Because of the noise, these two ground may not be at the same potential, so there can be some noise voltage between these two. Why this noise voltage? Because you know some electromagnetic wave is there, it is just passing through this, so the electromagnetic flux is linking this conductor, etc. So some EMF will be produced. So EMF will be produced means across this conductor there will be some voltage. So therefore if two ends of this they are connected, there can be a voltage difference. So what will happen if these two are connected? So there will be some current flowing through there. There will be some current flowing through this. So that current, that noise current will create additional drop in the wire. So whatever may be the voltage you are measuring, some noise voltage drop will still be there. So that is why if you make two n, they are both n grounded, there will be a loop for circulating current of the noise because of the noise. So to avoid that, what is usually done is this one. That means here the ground is not there. The ground connection is removed here. So here you can think of it is a floating. So there is no ground. So this is one way of doing things. So usually as electrical engineers, we prefer grounding at both the ends, but it is not always very good for measurement. So this is the thing we should be careful about. This is another thing. See the shielding and body that is grounded. So that's what I am telling. Here, there will be some circulating current through this body. That circulating current, if this is connected, so the circulating current may flow through this conducting or your signal wire. So signal wire will have some additional voltage drop. So the amplifier, whatever the V output you are getting, the additional voltage drop that will be included. So that is why sometime you also cut something here. The shield is cut, here the ground connection is not there. So even if the circulating current tries to flow, it cannot reach this conducting wire or signal wire. So in this way, even if you are doing grounding at both the side, we have a small cut in the shielding also. That will also do. So this kind of a configuration we follow during the measurement. This kind of a shielding, another thing that we can follow during very delicate measurements. বলো এটাতে কোনো কোয়েরি থাকলে বলো যাক খুব খুশি হলাম কোনো প্রশ্ন নেই দেখে খুব ভালো ব্যাপার হ্যাঁ analog filtering you can do but it is not having very good pattern because filters are used for noise removal. You can design a band pass filter, high pass filter or even low pass filter to increase. We call it signal to noise ratio. Okay, signal to noise ratio higher means signal strength is high, noise strength is low, because in many cases we cannot eliminate the noise 100%. So we represent the denoising efficacy or efficiency in terms of signal to noise ratio. One important aspect of eliminating 1/f noise is modulation. Modulation, do you have the idea of modulation? Modulation মানে কি বলতে পারা উচিত একটু বলতে পারবে কেউ? Anyone? What is modulation? Say you are having a low frequency signal. If you modulate it, what will happen? The signal, amplitude modulation or frequency modulation, that will be on the high frequency. So that signal will be transferred to the high frequency. Okay, so high frequency signal, that means your 1/f noise has a high magnitude at low frequency. So if you transfer your signal from a low frequency to a high frequency and then you do a filtering, then what will happen? The effect of the low frequency noise we can eliminate. Otherwise, say your signal is low frequency, your noise is low frequency. So if you apply a filter of low frequency, then what will happen? Some part of the signal that will be eliminated. So if you modulate the signal, then the effect of one, then filter it, then the 1/f noise can be eliminated. এই আইডিয়াটা বুঝলে কিনা একটু আমায় বলো। এই আইডিয়াটা কি বুঝলে? So if you modulate it, the signal will be transferred in a high frequency domain. If it is transferred into a high frequency domain, the high frequency region, then you can filter it to eliminate the low frequency 1/f noises. শ্রেয়া কিছু বললে? শোনা গেল না। শ্রেয়াগিরি কিছু বললে? এই কনিষ্ক, আমার কথা শোনা যাচ্ছে?
হ্যাঁ স্যার।
ওকে, তাহলে modulate, if you modulate a signal, say if you are using say a frequency f0, if your carrier frequency is fc, the signal will be transferred fc plus f0, fc minus f0. So therefore we can eliminate, we can set a cutoff at a low frequency so that we can pass on the high frequency and eliminate the effect of 1/f noise. বুঝতে পারলে কি বললাম? So modulation is an important thing. The similar signal chopping is also sort of a pulse width modulation you can think of. Lock-in amplifiers are also there. Lock-in amplifiers can also eliminate. Lock-in amplifiers I have discussed in elective, those who are having that measurement elective, in that case you learn the lock-in amplifier. But okay, lock-in amplifier details, they are not required. Lock-in amplifier principle is simple. Principle means you are say are having a signal with some noise. So from the Fourier series expansion, you know that it can be, think of a sum of so many sinusoids. So in lock-in amplifier, one particular frequency that can be picked up. That frequency, it is a locked frequency. At that frequency, you can extract that particular signal. Okay. So even if you are having say so many frequencies, if you are interested in 50 Hz only, you can extract only 50 Hz, eliminating all others. That is called the lock-in amplifiers. And there are software methods also. They are the hardware filter, but it can be implemented in software also. Say you can sort of averaging, boxcar averaging or ensemble averaging. Boxcar averaging means, say, what is the difference between this boxcar averaging and ensemble averaging? Say this is a signal V versus T. So you are having a signal like this. Now, if you apply a filter, window, say we are having a window like this green window. So up to this much, you are taking the signal and take the average of all the sample signals. Then shift it towards right like this. Slightly shift, then again take the average. Then again shift it towards right. So you are slightly shifting the window and taking the average. So if you are having a random signal, zero mean random noise. So if we are averaging, so the average of those random noise will be zero or they will be less. So therefore, if you take the average using this sliding window or boxcar sort of, this is a boxcar, this box or window. So the effect of noise will be eliminated a bit. এই প্রসিডিওরটা কোথাও আগে পড়ানো হয়েছে অ্যাভারেজের এটসেট্রা? অ্যাভারেজের পড়েছো কোথাও?
No, sir.
We have done a lab on it. Like we were told to do that boxcar average.
Yes. In which lab? Control.
I don't remember, but they were told to take some random samples like a signal and
yes, take a boxcar average. Yes, this is the boxcar averaging means this one. That means say you are having samples. Say you are having samples, these kind of samples, and you are taking say a 3-window boxcar, 3-sample window boxcar. So 3 sample, you take average, then shift it 1 sample, then again next 3 average next 3 samples, then again next 3, and so on. So if you average if it is a random noise, the average of the noise, if it is a zero mean random noise, so therefore there will be some, if you take the average, the effect of noise will be zero, eliminated. Okay, this is the basic idea. বুঝতে পারলে কিছু? At least some idea why it is called the boxcar and
Yes,
what does
sir.
it mean?
Sir, what does the size depend upon of that box?
That is
Or the window?
that depends on your that noise nature and the signal window. Okay, so that is a trial and error method. Okay,
Okay, sir.
sometimes trial and error method is a good name. That is called Edisonian approach. Okay, but those who are follower of Thomas Alva Edison, they don't like it, the term Edisonian approach. Sometimes we call it trial and error method as Edisonian approach, because Edison invented so many things by trying so many methods, procedures, sort of a trial and error method. Okay, mixing this with that and so on. But that is not the true way of learning. But by trial and error, that is another method. So you have to vary the window of the boxcar slightly from a low value to a high value. Then you have to check on at which value of the window length your performance is the best. Then you have to choose that one. Okay. Now the ensemble average is just something different. That means, say you are able to record your ECG signal say so many times. So the same ECG of same person you have recorded say 100 times, 50 times, 20 to 200 times. Okay, whatever possible. Ensemble average means you are taking the average. Say this is time t. Say this is time t. You are taking at time t the sample values of all the realization and take the average and put it like this. So again take another time instant. Say take all the values, all the signal values at that time instant, take the average, and that will go. So after some time, if you take the average at all the time instant, you will get some signal. So that is we are talking about the ensemble average. Okay, it is not like the boxcar average. ঠিক আছে বলো, বুঝতে পারলে কিছু? What is the difference between ensemble average and boxcar average?
Yes, sir.
Okay. And also you can apply the digital filtering, that digital filter that is already covered in your DSP. But a hybrid method, in most of the cases, they will be fruitful. You can go for a first stage of elimination using hardware filters, then software adjustments. Okay, so this kind of hybrid filters, they are also being used. So up to that, I have planned for today. Now, tell me if you have any question regarding this one. যা পড়ালাম তাতে আর কোনো কোয়েশ্চেন আছে বলো। ঐশানিয়ার আরেকজন যেন কে, আরেকজন ছিল কি যেন নাম, সাথী বোধহয়, তাই না? এরা দুজন কেটে পড়েছে, খুব ভালো।